Hello, Arijit. Arijit. Is it Sairam giving technical support this evening? Or is it Ravi? Hello, Arijit?
Hello, sir. Good evening.
Hello, Arijit?
Hello, sir. Am I
Yes,
audible?
yes, yes, yes,
Okay,
yes, I
okay.
can hear you. I just wanted to know who is recording the lecture, this evening's lecture.
Who is recording it? I think somebody from the ISER team.
Yeah, so I just want to make sure that it is being done.
Right, right.
Because I got some message about the recording and I don't know why I received that message.
Usually, when they activate it for recording, there is a pop-up for everyone actually.
I see.
Yeah, yeah.
Yeah. Okay. So
I think maybe Sai is there from ISER Tirupati side, right?
yes. So I thought that it might be Sairam, so I called his name out, but I did not get a response. Maybe he did not hear me.
I see. I see. Okay. Sunil is here. Sunil, hello, Sunil.
Hi, Arijit. Yeah, I was not able to unmute myself.
Right. No, I understood that probably it was an issue with the microphone not being.
No, I mean, I was not made as a co-host.
Right.
Yeah. Okay. Yeah, now it's fine.
Okay, great.
Yeah, the problem is that even if you are made a co-host, if you lose the internet connection,
right.
Yeah, that is a problem.
then you lose that privilege, and then you are not able to. I had this difficulty yesterday evening quite a lot.
Correct.
Yeah, I think it is probably we can just allow everyone to speak. That may be one way to sort out this issue, because right now only co-host can unmute themselves.
Yeah, I think it is a good suggestion, because the number of participants is not large and they are all who are actually interested in the field. So I think that should work very well.
Yeah, I think usually it's within 50 numbers, so we can probably do that.
Yes. So do you want to
I will tell Saira.
Yeah, that's good. I think it's a very good idea.
Professor Ambika is also here. Good evening, Professor Ambika.
Yeah, I think she also has the same issue, I guess. Right.
Yeah, good evening, Professor Ambika. I think they're trying to unmute everybody.
Okay, Professor Urbasi Sinha also joined.
Hi, good evening.
Yeah. Good evening, Professor Ambika.
Yes, good evening.
Good evening, Professor Ambika.
Good evening. Last 2 days I couldn't join. I had 2 other commitments.
Yes.
So our speaker, Professor Urbasi Sinha, is also joined. Yeah, she is also joined.
Yeah. Good evening, Professor.
Good evening.
Good evening.
Yeah. How are you, Arijit?
I'm fine. How are you?
I'm fine, thanks. Let me just try and open my presentation and do a screen share.
Right.
Yeah.
If it's okay with you, you can activate your video. Yeah.
Great. Yeah. So I'll just share screen and hope for the best.
Yes.
Usually it works.
Yes.
Okay. I think it is doing okay. So I'll.
It is up. Yes.
Absolutely.
I'll now unshare. Yeah.
You can do a full screen probably, and we can check it out quickly.
Yeah. Sure. Okay. Zoom is good.
Absolutely fantastic.
Okay, so let me do that.
One non-Google product which lives up to its standard.
Yeah, but we can't use it in official things in Government of India.
Yeah, that's true.
But thankfully, this is not Government of India.
Right.
So it's working, right? Like.
Absolutely. Yes. It's working.
So should I now stop sharing or?
Yeah, you can stop sharing.
Yeah.
Just give me a minute and it should be fine.
How's the situation in Tirupati? It's
it's not too bad. It's progressing on the positive side. But
progressing on the positive side means it's negative.
Well, not in terms of cases, but in terms of recoveries.
Okay.
So we are also bringing students to our campus back in batches, and things are looking good. So that's a positive side, I would say. And we are also a bit cautious because given what happened in April to June period, we are not taking any chances.
I know that is the part which, I mean, we are thinking twice before doing most things.
Right.
But then hopefully normalcy of some kind will happen soon. And yeah. Anyway, I'll stop my video for now, I think.
No, it's okay. It's okay.
It's okay? Yeah.
Yeah, absolutely.
Yeah.
So how is the situation at RRI? Is it good?
Well, it's, I mean, at the moment it is okay, but we did have a pretty rough patch around April, May. Well, of course, we also had a lockdown. So
right.
But then there were quite a few people who were affected, and
I see.
And one couple of people passed away.
Oh,
maybe you will remember them. This. But then, yeah, they're from the the admin side.
Yeah. I recall seeing a condolence message.
Yes. But then at the moment, it is touch wood.
Okay.
Yeah, but we have to just wait and watch.
Okay. And lab people are coming regularly to the labs, and
at the moment, so I think only around 10 days back we were told that we can. I mean, that before that it was a roster system.
I see.
So only in an air-conditioned space, only 2 people at a time and all that.
Oh, okay.
So only 10 days back we were told that we could leave it to a little bit to our discretion if 3 is, I mean,
little
more than 2.
Little more than 2
can be, and so at the moment that is what is the current policy.
I see. I see. Okay. That's something positive to hear. Okay, because otherwise entire activities get stalled, right?
Oh, it is terrible. Especially experimental, as you know.
Yeah.
And also, it's not like if you have a stoppage for 2 months, you come back and everything is behaving the same way.
Yes. Unfortunately, it's not like that. You have to retune everything.
Yes.
It is very true. This COVID is taking a huge toll on the entire community, and it's really very hard to get back.
And there are also other issues, like some students. I mean, it's also affecting them.
Mentally, correct.
So they are a little bit jumpy. 1 or 2 of them more so. So
yeah.
I mean, I also feel jumpy, but then when I look at them, I'm like all very, fine.
I think we just got to hold on to nerves, right? I mean, we
as much as possible, we have to do that, right?
Right.
Sometimes it's quite bad.
Okay, so maybe we'll wait for a minute.
Yeah, it's almost time, I think.
Yeah, we'll just wait for a minute, and then maybe Professor Vishnu can initiate the proceedings for today, and we'll start from there.
Okay.
Arijit, I think we are good to go.
Yeah, I think so. Let us proceed.
So, Professor Urbasi, Sinha, are you fine? Shall we begin the session?
Absolutely. Thank you very much. Yeah.
So, first of all, thank you very much, Professor Sinha, for accepting our invitation. It's wonderful to have you here. And this is the 3rd evening of the anniversary week Colloquium series that we are having at the Center for Atomic Molecular Optical Sciences and Technologies. And today's talk on photonic quantum sciences and technologies is a very important one in this series. And it's absolutely great to have a scholar, a researcher, and a leader in the area this evening with us. And students who take a course on quantum mechanics with me are familiar with the paper Sinha, and Sinha. So they certainly know about your work to some extent. And it's a great privilege for all of us to have you this evening. let me request Arijit to formally introduce you to the audience. Arijit.
Right. Thank you, sir. So good evening to everybody who is on this occasion joined us to hear the special colloquium by Professor Urbasi Sinha from the Raman Institute in Bangalore. To briefly give a introduction about our speaker today, I will sort of narrate her academic journey and give an insight to what she has been doing in her lab and in her group at RRI. So she was trained as a physicist at the University of Cambridge, where she did perform experimental and theoretical studies on AC disruption effects in high-heat superconductors. She got involved in device fabrication in a clean room environment, as well as cryogenic measurements. Then for her first postdoc at Cavendish Laboratories, again in Cambridge, she worked on a fascinating paper industry-funded soft condensed matter project. Then I think over the last 10 years, she has been doing quantum optics-based experiments, primarily targeted towards testing fundamentals of quantum mechanics, as well as quantum information and computing. She subsequently did a second postdoctoral work at the Institute for Quantum Computing at Waterloo in Canada. And one of the most interesting pieces of that work was she was involved in the triple slit experiment, which served as a precision test for the Born rule for probabilities in quantum mechanics. At her lab at the Raman Institute, which is aptly titled as the Quantum Information and Computing Lab, the QUIC Lab, is a part of the Light and Matter Physics group at the Raman Institute. And her lab is an optics lab, which also has a class 10,000 clean room, which enables precision control on temperature, humidity, and dust particles, which are absolutely critical to performing such sophisticated experiments on photonic quantum technologies. So with this environment, she has performed several precision experiments over the past several years. And today she is going to give us an overview on her work and on the future work that she is going to engage in, and perhaps also share an overview of what photonic quantum technologies holds in India and in the global context. So without further delay, I invite Professor Urbasi Sinha to enthrall us with her colloquium.
Thanks a lot, Arijit, for this very kind introduction. And of course, thanks to Professor Deshmukh and all of you there at Camost for this kind invitation to present a colloquium to you here today. Well, it's very nice to actually have this the center come up, and I'm hoping that there will be more interactions between our groups in years to come. So I will share my screen, and of course, again, it should work. Yes, it is doing that. Yeah.
Yes.
Okay.
Yes.
Yeah. So, before I begin my talk on quantum science and technologies with photons, I would like to say that it gives me special pleasure that Arijit is hosting this talk, because when I first joined RRI, Arijit was a senior PhD student who was just about finishing at that time. So it was very nice, to see that. It makes you feel a little old. But then it is a good old, right? Like when you see young colleagues who have now, come up with their own labs and their own faculty positions, it's all very heartening, and it makes you feel that there is things to look forward to. So I'm very happy that Arijit is, doing so well. So thanks a lot, Arijit, again for this invite. So with that, I would, you can hear me well, right? Because that's the usual first question people ask in Zoom seminars.
Yes, you're absolutely audible.
Great, yeah. So as was mentioned, I would be giving you sort of an overview on quantum science and technologies with photons, and of course talking a little bit about stuff that we are doing at our lab at RRI, and this is going to be more like a flavor of various things that we are doing and things that are happening all around, and hopefully for the young people in the audience, it would be encouraging for you guys to actually think of these areas as your possible future research directions. Okay, so with that, so basically the premise of whatever we do and whatever we will intend to do in future, it's kind of summarized in this quote which is, today's science is tomorrow's technology. So what we are doing is very much a marriage between science and technology. So we are very interested in fundamental aspects of, various quantum phenomena. And at the same time, this interest is also reflected in the technological applications, some of which we are working on ourselves, and some of which we hope that our work will actually lead to. And in fact, this quote is said in a certain context, and the idea is not to be too enamored by the context, but basically, to realize that it is all about this, a marriage between science and technology. And in fact, one of the things that has happened in recent times is this, declaration of this national mission on quantum technology and applications by our government last year. And so this is something very heartening because, I have been in India, in this lab for around 10 years now, but then there are many people who have been involved in specifically the theoretical aspects who have been at it for several decades. And so it's very nice to see that this work, in theory, as well as these experiments have actually led to this sort of a resource, promise and commitment, and sort of this faith in this field in general. And so, we do hope that this will lead to more science and technology come out of quantum in the next years and decades, right? So the big picture, of course, the big picture would be that our theoretical understanding of the universe is very incomplete. And so we don't understand more than 80% of what the universe is made of. Okay, and this we know that, most of it is what we call dark matter or dark energy and so on and so forth. So what this means is that it's very important for us to have a very precise understanding of at least what we do understand, and in some sense putting a bound on how well we understand things. And so that is why fundamental tests are very important, and especially in our domain, of course, which is quantum mechanics. So having precision bounds on various axioms and various theorems and various rules in quantum mechanics is very important, because these will then reflect in the technological applications that we put them to. And so this forms a very important and integral part of the kind of work we do, which is fundamental tests of experiment and theoretical aspects of quantum mechanics. Okay, and then of course, the two applications which we are mostly interested in, one of them is quantum computation. I understand that yesterday you heard some aspects of quantum computing from a superconducting qubit perspective, whereas of course we are working more on the photonic aspects. And then we have quantum cryptography, which is of course one of the main areas where photons have very little competition, and this is what would guarantee perfectly secure communication. So our lab deals with experimental as well as theoretical problems relating to fundamental tests of quantum mechanics, quantum computation, and quantum communication. Okay, and so we have around 50 minutes to an hour, so there's not much, a lot that I will be able to tell you. And so please do feel free to visit our website, where we tend to put in details of things we are working on, so that the students especially can read a little bit and maybe ask questions through email and so on and so forth. So, well, of course, a lab is a lab because, of the people who are in it. And so we have different types of people. We have postdocs, PhD students, as well as, engineering stuff, because we have certain projects in which there is a lot of requirement for both scientific as well as engineering skills. And so many people have come and gone to, different countries and so on. So this is a snapshot of various experiments in the lab. Let me just try and get this laser pointer to work. Which I think, yeah. So, so this is a snapshot of different experiments, and of course, hopefully we'll have visits and all soon. But at the moment, this is how things would look on a usual day. And for the students specifically who may be interested in knowing more about, these photons and how to make them, this review article may come in handy. I mean, so when we say that we're working with photons, of course, we're working with single particles of light. And you would say that, that should be very straightforward. You have light all around you, you just make it dimmer and dimmer, and you would reach a single photon level. But that's actually not true. So you just don't reach that by doing just that. And so there are different dedicated technological approaches towards making these single photon sources. And so this based on nonlinear optics, some of them based on quantum dots, atomic sources, you have NV centers. There are different approaches. And so it would be nice if, students actually had this holistic idea about the different ways of making these, because it's not just just doesn't happen naturally. So you have to work towards getting the single photon. For instance, this is a snapshot of, some of the photons from our lab. And so this, we are working on what is called spontaneous parametric down conversion. And that's a nonlinear optics process. What it does is it actually, in a nutshell, it basically, you have a single photon, which is called the pump photon, which actually generates 2 more photons, which are called the daughter photons or signal and idler and so on. And so this is a pair photon source. One pump photon gives rise to a pair of photons after this nonlinear optics process. And it's not like every pump photon does it. 1 in 10 to the 6, 8 or 10, depending on your crystal, will do that. But this is this is called down conversion, and this is the way in which we are creating our photons right now. And so they come out in the form of cones. Okay, and so you can see, this cone on the right and the cone on the left. Just Arijit, can you confirm that you can actually see my laser pointer? Because otherwise I'll change my...
Yes, I can see.
Yeah, okay, yeah. So this is the cone on the right and the left. And so basically, if one photon is here, the other guy will be here, so that you have energy momentum conservation. But then this particular point, which is the yellow one, that is the interesting one, because you don't know which cone it a priori belongs to. And so this photon, so if there are 2 of them, if one of them belongs to the right, the other guy belongs to the left. But otherwise, you don't know. And this lack of information is actually reflected in these photons being what is called entangled photons. Okay, and so they actually describe a state where you can't describe them as a product or a separable states. Okay, and so this is a picture from our lab of entangled photons. Now, I will discuss some of the applications that we are working on in a little more detail, but just to give you a snapshot in the beginning. As I mentioned, one of our main areas of focus is fundamental tests of quantum mechanics. And in fact, already I was told in the beginning by Professor Deshmukh about the paper that already some of you may be aware of. So I will be talking a little bit more about that work as well. And so that was on the superposition principle and bond rule and fundamental tests of these principles. Okay, and so here we have some fundamental quantum optics experiments. And so if you've taken a course in quantum optics, you know what is called the Hongo-Mandel effect. So essentially about the 2 indistinguishable photons exiting a beam splitter either one way or the other, and not splitting up and giving rise to a dip in the cross correlation. So this is something which, of course, is one of the standard workhorses of quantum optics. But what we went on to show is that we can get 100% Hongo-Mandel dip by using classical sources with phase control. And so if you have interest in this, do have a look at this, because it's very interesting. We actually challenge the use of the Hongo-Mandel as a marker for quantum. And we say that, we can actually get a Hongo-Mandel dip to be 100% from classical sources. So you have to do something more. You have to actually work on what is called the complementarity test in order to have a true signature of quantum. I'll go on to this one a bit more in detail. And another thing which we are very interested in is, of course, entanglement. And this is something you have already perhaps heard of. Entanglement is a quintessential quantum correlation. And so what we are doing is we are studying various properties of entanglement, both static and dynamic properties. So in the dynamic property, there's a very interesting one that, entanglement is a correlation, fine. But then as any other thing, there is also interaction with the environment. Okay. And so this correlation decays as a function of time. So for some classes of systems, the correlation drops to 0 at a finite time, and that is called sudden death of entanglement. And so what we have done is we have come up with schemes to delay the onset of sudden death, or avoid it altogether, which of course is very beneficial because it tells you that, you can hold on to this entanglement for longer, which is what you would want. So that you can do your computing or communication or whatever it is that you want to do. And so this is the experimental setup. And, actually, as of today, we have just about finished also the experimental implementation. This was the theory work that you see, but we've kind of just finished showing that this actually works. And so a first proof of principle experiment has just been completed. Now, going on to another genre, which is of a lot of interest to us, this is the measurement itself. Okay, and so anybody who's working on quantum mechanics, you would know that one of the long-standing, what should I say, topics of discussion and debate is the quantum measurement problem. So as you know, you prepare a quantum state, it evolves, but then when you measure, you essentially basically just it's called collapse the wave function, which means that is a non-unitary step. So you can't reverse it. And this has been a problem, and this has been something which people have been trying to resolve in different ways and so on. But one of the interesting aspects of measurement is that there are also things called generalized measurements or weak measurements, where, it is not like the conventional strong measurement. So just to give you a flavor, so what happens in a quantum system, which is one of the most important aspects, is that you prepare a quantum system, it evolves, and then if you interact with it, you change the system, right? And so you don't have the same system anymore. And this is also used, in catching an eavesdropper, for instance, in communication problems. But then that is a strong measurement thing. If you do what is called a weak measurement, then you can weakly interact with the system, and in a statistical ensemble way, you can gain information about what is happening to the system between preparation and measurement without disturbing it. And so we have used this to do very interesting things like, infer the expectation value of a non-Hermitian operator. And very recently, we have done what is called, the first loophole-free, unambiguous demonstration of the quantum Cheshire cat. So maybe I won't get into the detail, but it's a very interesting area where you can do many things and learn many things about quantum mechanics in this ensemble manner. Okay. So now going on to a little bit more detail about some of our applications. So first one is our approach to quantum computing. Okay, and so quantum computing, of course, you've already heard of, so you know what in general this is supposed to promise and so on. But what you have encountered so far is quantum computing using what is called qubits, right? So two-level systems, you have two-level systems, they can be formed from the two, levels of a Josephson junction, it could be the two levels of an atom, it could be the horizontal and vertical states of a photon, many ways in which you can define two-level systems. But then one of the long-standing things which we have been trying to get in terms of the qubit-based quantum computing is a higher number of qubits which are in a coherent superposition, right? So you may know that the number which we were really after for a long time as a community was 50 qubits. Okay, so we said that, if we have a 50 qubit quantum processor, then we have, the first level where we can say that we have something where we will be able to demonstrate certain things which the classical counterpart may not be able to easily do. Okay, so 50 was a holy grail for a long time. We have achieved this 50 as a community. So there are two or three companies in the US and one demonstration in China where they've actually been able to do this 50 and slightly greater than 50 demo. But then what is this thing about 50? The thing about 50 is it gives you access to 2 to the 50 dimensional state space, right? The 2 to the 50 is what you really are looking for. This large number, which is supposed to be equivalent to the age of the universe. Even. So this 2 to the 50 is what we wanted. Okay. So now think about it. If instead of 2 to the 50, why 2? Because of the two-level system, right? So now if I went on to systems which have more than 2 basis states, say 3, 4, or 5, then the 2 gets replaced by these numbers, then the exponent also drops. So instead of 2 to the 50, you can have, let's say, 3 to the 33, and so on. So by a smaller number of systems, you can define, same complexity of state space. And so that is the basic reason why we would be interested in exploring higher dimensions than 2. And that is what is called qubits, where D is essentially replacing the B, where N is greater than 2. And so we have in our lab our own, indigenous system of bipartite qubits, which is basically a set of 2 qubits, which we have shown, evolved using our own technique called pump beam modulation, which I will get to a little bit. So this is the idea. So qubit has 2 states, qubit has 3, and so this is essentially it. So you form this alpha 0 plus beta 1 plus gamma 2. So one way of doing this would be that if you have a single photon incident on a triple aperture system, let's say, then you do not know which aperture it will go through a priori. So it defines a superposition by the spatial degree of freedom. Okay. So what we have done which I'll come to. And so you get the idea of why increasing the number of dimensions has an advantage. For instance, if you want to say something which involves 4 results, so you will need 2 qubits to do that. But in case of a Q quad, you will need only 1. Q quad is a 4-dimensional counterpart. Okay, and so there is, in the spatial Qubit domain, there is previous work, including my own, which was done earlier on when I was at IQC. But what we have devised at RRI is this new way of generating qubits, which is called the pump beam modulation technique. So the essential idea is that instead of actually having these photons which are generated from down conversion and then having them go through slits and defining higher dimensions, we have actually modulated the pump itself and made it into a higher dimensional system, so that the daughter photons that are generated automatically carry the properties of the pump through. So it's like, the daughter carries the properties of the parent through, literally here. And so this is the, the image. So I will show you. So this is our setup, and I won't go through the details, but this is what it looks like. But essentially, this is the idea. So if this is the pump profile, usually it's Gaussian, so we transfer the Gaussian profile usually in down conversion. But then here, if the pump profile of the crystal is this, which is our actual profile, then this is the single photon profile at the detector. So you can see it faithfully carries this through. Okay, and this is the technique we have devised, which is pump beam modulation. Okay. And so we have actually shown that our pair of qubits has a very high degree of correlation by this standard correlation measure. 0.9 is a very large number if 1 is the maximum, because in experiments you never get something to be 100%. And so this is a very high, strongly correlated pair of qubits. Okay, so we have a novel system which is highly correlated in the spatial degree of freedom. So, but then the question is, while there are spatial correlations, how do we know if these correlations are classical or quantum? So we could do an entanglement witness measurement to certify or not certify entanglement. But what we have gone on to do is better. We have actually devised our own measure of entanglement, whereby we can use statistical correlation measures and actually relate them to standard measures of entanglement like negativity and entanglement of formation. Now, I won't get into the details because that's a bit technical, but you can find the references here if you are interested in this from a technical point of view. And so this is, how our profiles look. You can see it's a very nice correlation. So when the photon is from the first slit, then you have the correlation there, second, third, and so on. Okay, and so this is the interference profile. And very recently, and as we speak, as I've said that, it should be on the archive pretty much this month even, and which is not too far from now, we have derived, a monotonicity relation where we have generalized it to all qubits. So earlier we had restricted it to qubits alone, but now we know how we can, measure the entanglement monotones for any higher dimension. Okay, and so we have done a first direct measurement of an entanglement monotone. And we have also gone on to see that these measures are not equivalent. And this is the first experimental demonstration of this. So we're very excited by these results. And this will basically lay the foundation for using these higher dimensions towards various applications which we have in mind, including computing as well as communications. Okay. And so we are working on certain aspects of computing with using these systems with collaborators in India and abroad. And we've already shown some results which towards linear optics quantum information using these systems. Okay, and this is a nutshell for the same technique. And in fact, for the students again, some of it may have been a little bit technical. So you can again find a very, I don't want to say very nice, but I think it's a popular level exposition of this matter. Where, in this article that I was invited to write, where I've given again a holistic picture of these higher dimensional systems in our lab. Okay. Now I go on to another, development, which is connected again to both computing and communications. And so, when we talk about quantum mechanics, what is the first thing that perhaps comes to your mind? And I would say that, for most people, you would think of psi, which is the wave function. Somehow that is the first thing which you would perhaps think of. When I say a quantum state, you think of psi. So essentially, indeed, that is true, that is the most fundamental element, right? So you prepare a quantum state. After that, of course, you do things with it. you can do communication, you can do sensing, you can do metrology, whatever you want. But then first you have to begin with preparing a quantum state. But then now, when you've prepared a quantum state, and as I mentioned 5 minutes ago, one of the things is that in a quantum system, if you actually do a measurement, you change the state, right? So how do you know what you have prepared? So quantum state estimation is a very important problem. Okay, so if you do not have an idea about what state you have prepared, then it's very difficult, for you to put it to something further, like, come up with relevant gates or, key distribution, whatever it is you want to do, you have to know what you're starting with, right? So the conventional way of doing that is what is called quantum state tomography. Okay, and so tomography is actually something which is related to the CT scan. And I guess nowadays, after the second wave of COVID, all of us have a fair idea of the CT scan. Somebody or the other we know has had it. And so what is a CT scan? A CT scan, T stands for tomography. Okay, so let's say if it is your brain that is getting imaged, so you take different projections of the brain, you have different images, and then you reconstruct the image of the brain from these projections. Okay, so that is what is called tomography. So you have different projections and you reconstruct. Same thing we do for a quantum state. You actually project it to different projections and then you reconstruct the quantum state, because if you just try to measure it directly, then you might change it. Right? So, but then problem with quantum state tomography is that as you increase the dimension of the system, it scales as d square. So essentially, if you go to a 3x3 system, it goes to 81. So the number of measurements that is required scales with d square. And that is a problem. So it becomes very unwieldy very, very quickly. And so what we have done is we have come up with an alternative technique, which is called quantum state interferography. Experiment was done by us at RRI, and our theory collaborator is Arun Pati, who's from HRI Allahabad. And so this is an alternative technique where by using interference, interferometric method, using which an unknown quantum state can be inferred from the visibilities, phase shifts, and average intensities obtained from a number of interference patterns. So you don't need to do, keep changing the setup. So in tomography, you have to, change your operator to define the different projections. So you basically have to keep, changing your operator, and you have to do basically new experiments. Whereas here you do an interference experiment, no need for changing anything in your setup. And from this interference pattern, you will be able to get the unknown quantum state. And so this is, a single shot quantum state estimation tool that we have devised. And this is the basic idea. Again, I won't go through the maths and all in too much detail in this talk, but then essentially this is how we've prepared an unknown state. And we have actually gone over the entire block sphere. So we have shown this for arbitrary states. Okay, and so you have an interferometer, and by performing certain operations, so which I will come to, but then basically the point, as I mentioned, is that quantum state tomography requires d square minus 1 measurements, whereas QSI, that is quantum state interferography, it requires d minus 1 interferograms. So we have actually, changed the complexity class of the problem. So essentially for d equal to 2, which is a qubit case, you require only 1 interferogram, which becomes a single shot state estimation. So this is the general idea. Okay, and so now this is your unknown quantum state. For a mixed qubit state, you know that there are 3 things you need to determine: the theta, the phi, and the mu, and all of them can be determined from an interference pattern. Okay, and so this is how it works. So you have certain operations which we define as the projection operator, and this is the Pauli X actually. And so if you go through the math, you will realize that the interference intensity is essentially this. Okay, and so by measuring this, the value of the epsilon for the maximum intensity, you get the phi, and similarly the average intensity gives you the theta, and the visibility will give you the mu. Excuse me. So by measuring an interference pattern, you are able to get all these 3 parameters which are required for a mixed state, and for a pure state only 2 are enough, right? And so this is the general picture. Again, I'll skip the details, but some of the results. So now this is important. So you have the pure state and the mixed state. So you can see the fidelity with which we are getting our pure state estimation is close to 99%. And for the mixed state, it goes between 90 and 98 because mixed state involves one extra parameter where, sometimes the pole is coming in and that reduces it a little bit. But then having said that, this is very comparable to quantum state tomography, but then of course with much less number of resources in terms of the number of measurements that you need to do. And so that is QSI, and we have shown how it can be used for higher dimensions as well. And that is where the true advantage also comes in with D-1. When D becomes greater than 2, then of course the square and the linear really start playing a role. And we can also use this to measure the entanglement of a bipartite system. Okay, let's skip the math here. But then essentially it's a single shot measurement. We can use it to quantify entanglement, and it has really a fantastic scaling advantage over the conventional state tomography. So now this is very nice. But then what is also very nice is, as a future thing for this is that we have shown how we can actually do this in a miniaturized manner. So while we have of course demonstrated this in a tabletop experiment, quantum state interferography is something which is actually lends itself to being miniaturized, and we can actually conceive of a box. If you use integrated photonics, for instance, then you can have a box where you have the unknown quantum state as the input, and the output from that box is your answer to what is the quantum state, because you don't need to change any settings. So once you have set it up and then you have boxed it, you don't need to open it again and again. And so in fact, you could have a small device to measure the quantum state. This is something that would be very interesting in a future work prospect. Going on to the experiment, which already was alluded to in my introduction, which is about the theory and experiments on quantum superposition principle, Born rule, as well as higher order interference in quantum mechanics. Now, again, changing the gear a little bit, I talked about quantum state estimation, I talked about quantum computing. This one is, of course, on the superposition principle, and as you know, that forms the basis for quantum computing. So superposition principle is the reason why we have this more than two possibilities. So alpha 0 plus beta 1, where alpha and beta is anything on the Bloch sphere with the normalization condition. So now what about the superposition principle in double slit experiments? So here you have a double slit scenario, okay? And you have a source here, you have a detector. This is a very common, system, right? I mean, we always talk about the double slit as an example whenever we want to discuss anything quantum, really. Yeah. So you have a source, you have a detector, you measure the interference. Now, what is it actually that we are doing? So you have a source, you apply a certain boundary condition to it, right? Like it's a boundary value problem ultimately. So just like you have your potential well, potential barrier, a double slit is also a similar boundary value. So now what I'm saying is, if I actually close the slit B and only open slit A, then it will have a certain solution. You have a certain source, it is going to reach here and it is going to have a certain solution. Let's call that solution psi A, okay? Now, if I close A, open B, I can call the solution psi B. The question that we ask is that if I now open both the slits, is the solution psi A plus psi B? And of course, this is what we have been using in all these very important books, as well as, we have been doing this in our own work for all the time now, right? That psi A plus psi B, so mod psi A plus psi B whole square will give you the interference pattern. But then you question it once more, that is this really true? That is this really complete? And of course, the answer to that after all this, discussion had better not be yes, because, then it's not a very interesting question. But then the answer is, of course, no. And why is that? Because psi A is a certain boundary condition. Okay, psi B is the solution to a second boundary condition. And when you open both of them up, it's a third boundary condition. So superposition principle means that, you have a solution A, you have a solution B, then alpha A plus beta B is also a solution, provided the boundary condition doesn't change. So here you have changed it. So you just can't add it and say that is all there is to it. Okay, and so in fact, if you follow Feynman path integral formalism, it becomes even clearer. And even if you don't, you can just, this is a very nice diagrammatic way of looking at it, that, Feynman paths are, of course, probability amplitudes. And so in this work, Yabuki showed that, other than these conventional straight line or classical paths, there will also be paths of this kind, which will only happen when both slits are open. Yes. as you can easily make out. If I close this, this won't happen. So these sort of contributions do not happen in the single slit open scenario. And these are the ones which add a correction term to this psi A plus psi B, okay? Because according to path integral, it is an integration over all possible paths that can be taken by the particle in going from A to B. And so now if you think about it, if you apply it to the slit problem, you will see that it's not just psi A plus psi B, you need a correction term. And so going on to the triple slit scenario, in a triple slit scenario, you actually have a situation where you can define a quantity which would be 0 if it is simply psi A plus psi B plus psi C, and it will be non-zero if it is not. Okay, and so the first triple slit experiment that was done, in fact, I was also a part of that, where we had actually used this as a test for Born rule for probabilities, because as you realize, there are two aspects to this. It is mod psi A plus psi B plus psi C whole square. So it is not only whether it is psi A plus psi B plus psi C, but also whether it is whole square. And so this whole square was questioned in this experiment, and we found that, we put a bound to Born rule through this experiment. But then we never asked whether psi A plus psi B plus psi C itself also holds. And so that is what we went on to ask later, and in our work here. Which was, from RRI and in collaboration with from IISc as well. And so this is where we showed that, in fact, we can define a quantity which would be a non-zero if this simple naive application of the superposition doesn't hold. Okay, and so this was the theory work, and in fact, this work had analytical details of the same. An experimental work which happened almost in parallel to our own experiment was by the Boyd group, where they actually said that, they have done an experiment to actually prove our theory, that they have found a non-zero term and the correction to the superposition principle using photons. And so this is how they did the experiment, where they had these single photons, and these slits, they were etched in a film which was made of gold. Okay, so obviously a very rich group, but then the gold actually added more than just the richness. It was basically something which leads to the production of what is called surface plasmons. And these surface plasmons enhance the interaction between neighboring slits, leading to a non-zero value for this quantity. So it was not quite a geometry-based one, but a material-induced one. And so this is what they went on to measure. And so now you can see that, these round circles here, this is their experimental data. And they found that, this is the variation of this parameter is called the Sorkin parameter, after Raphael Sorkin, who actually first introduced this for the Born rule test. Okay. And so the Sorkin parameter is varying as a function of detector position. And this line that you can see here, this is the theory curve that they plotted from our theory. And the claim is that these blue dots are a good fit to this blue line. But of course, if you were to be, if you were young, for instance, you would ask this question that, I could just fit this with a parabola. Why exactly do I need to call this blue line a good fit to this? And it's not a bad question, because see, there are no data points at the peaks or at the, slopes. So I would say that, the experiment that we did almost parallelly got published slightly later, actually does a better job, because, we have the value actually modulating as a function of detector position. And this blue band is our theory expectation, of course, our own theory expectation, and these are the experimental data. Okay. And so this is the first measurement of the non-zero Sorkin parameter in the microwave domain. Okay, and of course, with points matching every portion of the curve. And so this was actually done in an observatory 100 kilometers from RRI in an open field condition. So precision experiment in an open field with its own challenges, but it was a lot of fun. Okay. I was telling you about the Hongo-Mandel effect, so I wanted to give you a little bit of a thing for people, who may be from an engineering background. Maybe you will find this interesting, that we actually went on to do a Hongo-Mandel experiment using electrical pulses as opposed to optics. Okay, so as I mentioned earlier, the Hongo-Mandel effect is supposed to be a true effect of quantum, and two indistinguishable photons, they exit one way or the other, and it's supposed to measure photon distinguishability, and it's used as a test for photon sources to measure the indistinguishability of photons. And what we went on to claim is that it's not true signature of quantum. Okay. And I will, this is something maybe, you can have a look at a little bit later in detail, the math behind the homomandal. So you will see that, it is basically a bracket algebra and essentially the creation and annihilation operator. So this is the beam splitter matrix, okay? And so you will be able to show that, when these two photons are incident, so if they're incident from one side, then of course that is fine. But when they are incident, two photons are incident on two input ports of a beam splitter, what happens to the output is the question we ask. And if you follow the algebra, you will realize that they would either go one way or the other, forming what is called the 2-0 minus 0-2 state. So both go this way or that way. And so this is the state you end up forming. And when you measure the cross correlation with 0 time delay, you get a dip. And that is called the homomandal dip. Okay. But then in literature, you find that there is a lot of discussion about how a 50% dip, up to a 50% dip is possible for classical, and then above 50, it is quantum. Okay. And in fact, Hong O, Mandel's O, his thesis also says the same thing. Okay. But then what we found is that, in theory as well as experiment in this work, we have shown that by having a good phase control or a perfect phase control between your input pulses, you can actually have a 100% homomandal dip without, using photons. Okay, and this is very interesting because not only it gives us a very good control on the homomandal effect, which is in fact the mainstay for any quantum, teleportation and swapping and repeater-based experiments, but it also tells you that, it is not the ultimate thing in quantum. So what do you need to do? To do that, we'll tell you. So this is the 50% dip, which of course is fine. And this is our 100% dip from classical pulses. Okay. And this is the photonic version of the homomandal, which of course we also did, where we also got a reasonable 100% dip. So what happens now? If homomandal is not a true signature, then what do we do? What do we use the diagnostic for photon sources? So what we have said is that we have to actually do what is called a complementarity experiment, which means that instead of measuring just the cross correlation between the two outputs of this beam splitter, you complete the Mach-Zehnder or complete the interferometer and measure the interference. Because what happens is that if you have actual single photons, then you will have both the homomandal and the interference phenomena come through. But if you have classical pulses, you may be able to fool the system by having a homomandal dip 100%, but you will not have the interference effect. So interference will not happen along with homomandal for classical. So that is what is called the complementarity. Of course, that, the wave and particle nature together is what you are expected to see for a true quantum source. And so this is what we did using, actually, you can see, using completely electrical pulses. Okay. And so I'll skip the details, but that is what we went on to show, that complementarity is what you need to do. And so you can see this is one of those experiments and theory again, which is in the genre of precision tests of quantum optics itself. Yeah. Okay. So over the last part of the talk, I wanted to talk about something which is actually a very application-based, exploration, but of course based on fundamental quantum mechanics principles, right? So that is quantum communication, and of course the main quantum aspect of it is the key distribution, which is quantum. And I say that it is, the most quote-unquote practical quantum technology because, of course, while we are very, interested in quantum computing, the level of development in quantum computers is still at the level of the 50 or the 60 qubits. So, in order for it to actually come to the level where we would have the true quantum advantage come through, it'll take a little more time. It will happen, but not immediately. Whereas in the quantum key distribution, you already have devices which are available, companies which are manufacturing them. So there is a lot of practicality in that. However, having said that, there is a lot of fundamental aspects which are still left unexplored, which is to do with, how to exploit the system, exploit the physics better so that you can have more secure protocols, so that you can have higher key rates, lower errors, and how you can increase the distance. So there are many things there. So it, again, this going hand in hand. So certain things have been done, which is very nice, but there is, of course, a lot left to do. Okay. And so why you should worry about quantum communication at the end of the day? Well, of course, all of us are involved in at least 3 out of these 4 applications that I have listed here, whether buying something using a credit card, banking online, voting, and of course defense strategic communication, which is something in the purview of our defense sector. But all these things are examples of communication which is of a strategic nature. So whatever information that you are sharing has to be received by the intended receiver. You don't want your banking information to go to some random third party, because, you know, as academics, we don't have much in the bank, but we still value what we have. And so these are all examples of strategic communication, right? And so this is currently done using classical cryptography, where, of course, you know, you have this information which is actually encrypted using what is called a key. And then this is sent to the receiver, who also has a copy of a key, which he or she uses to decrypt the information. And then you have this happen in a secure way. But then the problem, so what is the problem with classical cryptography? What is wrong is a bit of a strong statement, but what is the problem? Problem is that unconditional security is not possible. For instance, one of the standard workhorses of classical communication or classical cryptography is what is called the RSA protocol. Now, the RSA protocol is based on mathematical complexity of factoring large numbers. What does that mean? So if I ask you, you know, what is 3 times 7? You will say 21 without even wasting half a second, right? But if I tell you what are the prime factors of 117381, you won't tell me the prime factors just like that. So factorization is a harder problem than multiplication, which is the basis for this protocol, which is used for our classical, you know, secure communication. But this gentleman, Peter Shor here, came up with what is called the Shor's algorithm, which uses quantum gates and can perform factorization in polynomial time, which means that it can change the hardness class of the factorization problem, making it much easier, provided you have the right quantum computer. And so then what happens? Of course, RSA protocol doesn't remain secure anymore, right? So computational resources grow very fast, and today's hard problem could be solved tomorrow using brute force attack. Okay, and of course, there could be new algorithms for classical computers. There is realization of quantum computers, which will run, for instance, Shor's algorithm. My security should be independent of future advancements in computational power, new algorithms, or new technology. That is, it should be future secure. Now, just to give you an example, let's say I'm leaving some, you know, resources for my next generation or whatever, and 30, 40 years down the line, when this person, you know, inherits it, he or she realizes that there is nothing left, because, you know, by then the quantum computer is real, and then Shor's algorithm has been employed, and all the security is gone. Now, that is a doomsday scenario which we don't want. So we want our security to remain so even in future. And so the current ways don't guarantee future security. And so that is why, you know, we need what is called quantum cryptography, where security is based on the laws of nature or laws of physics, and not on the mathematical complexity of a problem. Okay, and so most important part, as I mentioned, is the key distribution. So about the RSA protocol, one thing, you know, Krista Swore from Microsoft Research says that the RSA 2048 challenge problem would take 1 billion years with a classical computer, and a quantum computer could do it in 100 seconds, okay? But please remember that this quantum computer, which will employ Shor's algorithm, you know, to do this, would take around 4,000 qubits and 100 million gates to do that. So people who are working in this field never, you know, overclaim anything. So we would say that, you know, we are not quite there yet. We're not at the 4,000 qubits and 100 million gates level. But that doesn't mean that, you know, we can remain complacent, because the quantum computing research is going very fast. And so it could happen much sooner than you would think, maybe in 5 years, maybe in 10. Okay. And so you don't want to wait till then to find a solution. And that is why quantum cryptography becomes important and interesting even now, even though we don't have this capability right now. Okay. Because you don't want to make it become a problem and then find a solution. So in the domain of quantum communications, we have, you know, many ongoing projects. One of them is quantum experiments using satellite technology, which is actually India's first project on satellite-based quantum key distribution. This is in collaboration with ISRO. We are working on integrated photonics-based quantum key distribution under the ITPAR program. We have something called the Quantum Enabled Science and Technology Program by the DST, where we are working on long-distance quantum communication using teleportation, relay, and repeater technologies. And then again, we have a new project under the Center for Excellence in Quantum Technologies of the Ministry of Electronics and Information Technology. So we have a Center for Excellence in Bangalore, which is a tri-institutional center. So RRI is one of the institutes participating in the center. And so our project is on different ways of generating random numbers and also another way of performing fiber-based teleportation. Okay. So why do we need entanglement in QKD, by the way? We need entanglement because, you know, if at some level we stop, so if you just did prepare and measure based protocols, which is essentially like the BB84 and others that you hear, where you have a single photon based protocol, then you have to actually depend a little bit on your devices. And if your device is compromised, then of course you will not be able to go very far. So we want to reach a stage where we, can do things which are in a device independent way. And that is where entanglement comes in handy. Okay. Regarding the experiments at RRI Bangalore, regarding, in this domain of quantum communication, we have, of course, done almost every protocol that we could have done in QKD. So we have done single photon based ones where the security is based on the uncertainty principle. Okay. So this is our BB84 demo from 2017. And then this is a newer result where we have done a new version of the B92, where we have concentrated on increasing the key rate and the security aspects, which were missing in the original. So, in the to date, the best available B92 using heralded photons had a key rate of 31.6 kilobits per second and an error of 10.5%. And so ours, actually is much better than that. We have a key rate around 50 kilobits per second and an error which is restricted to 4.8%. Because in one of the things in QKD is that, it is not very useful if you have something which has an error which is beyond your security threshold. Okay, and so this is an information theoretic calculation that needs to be done for every protocol. And so if your error is beyond that, then it is nice, but not useful for security. So we have taken a lot of pains to actually ensure that we are below this security threshold, which is 4.8 for this particular protocol. Okay, and in fact, this particular experiment is indeed our country's first published experiment in free space QKD. Right. So now, of course, we have also done entanglement based QKD. And that is, this is an example of an entangled photon source. But again, I won't go through details, but these are your Alice Bob setup and so on. And we had very, very nice values of the entanglement. So entanglement, how do you know that you have entanglement? So you have to actually measure it. And so concurrence is a measure of entanglement. And while the highest possible value would be 1, we actually managed to reach up to this number, which of course means that, the protocol that we perform using this source would also have that level of security. And as I mentioned, this is the paper that we have published last year, which was this in-lab experimental demo, as I mentioned. Okay. So you can have a look at this. It's a very long paper, by the way, but then if students, I'm sure you will be finding something useful. The other thing which we did in this particular work, which is also worth mentioning to you a little bit, if you're coming from, let's say, a computer science background, maybe, then you would have a simulation mindset. And so what we want to do is also be able to simulate QKD, right? So if you're working on QKD, you want to set up your experiment, you want to have some idea about what kind of key rate and error you might expect from it. Okay, and so we know that there are different simulation QK toolkits which exist in literature. But the point is that, what we wanted is that, we should have a quick and precise simulation of physical processes considering realistic experimental imperfections, including the source, detector, noise, everything, and applicability to all existing protocols. So this is very important because usually the simulation toolkits and software available, they concentrate, they're probably developed by software developers. So they don't really care much about the fact that experiments are not really ideal. So we put in all this non-idealness into our development. And in fact, this is something which garnered a lot of, appreciation from different sectors, this particular work that we did. Okay. Going on to long distance quantum communications for the last 5 or so minutes. This is a quote that I would like to, take here by Isaac Asimov, of all people, that today's science fiction is tomorrow's science fact. So when we actually first proposed that, we wanted to do satellite-based QKD, and that was like 7-8 years ago, it was not necessarily something that decision makers warmed up to very easily. They felt that a photon, it is going to go to a satellite, and then we are going to have a key. All this seems literally science fiction. Okay, and so one of our neighboring countries in the last couple of years has managed to demonstrate a proof of principle demonstration of satellite-based QKD, and it is nice because that has led to a lot more interest in this, and in fact our project started in 2017 after this particular satellite launch in 2016, and so I would say that that is a very nice thing, because now it is a scientific exploration, and definitely is very much scientific. And so why do we need such things? Why do we need to go to long distances? Of course we do. What is the point of having secure communication where I'm communicating with my student within the lab? That is just great for proof of principle, but actually it is useful when neighboring countries want to talk to each other and things like that, right? Where strategic communication actually plays a role. And so ground-based QKD has a problem that you cannot go beyond a certain distance because you don't have line of sight. How horizon comes into the problem. If you use fibers, you have a problem because fibers, they have losses. So beyond a certain distance, you will need to amplify the signal under normal circumstances, which you cannot do because of no cloning theorem. So you have to think out of the box. And so there are, only 2 or 3 approaches of thinking out of the box at the moment. One of them is this trusted repeater approach, which is, this long kilometer networks where, you every few 100 kilometers, you have a trusted node, where the problem, of course, is you have to trust that node. You can also have quantum repeaters based on quantum relays and memories and so on. And then, of course, we have satellites for long distance. Okay. And so the idea of a satellite is that a satellite will spend some time on top of a ground station. It will exchange a key with that ground station. Then it would, in its pass over to a different ground station, exchange a key. And in the process, with some mathematical operations, these 2 ground stations will then share a common key. So these 2 don't need to be in their line of sight or anything. It could be thousands of kilometers separated, but satellite will act as a trusted node, trusted courier, and that is what will enable this communication. Okay, and so these are the different possibilities using different approaches. And the bigger picture, of course, is that we want to go towards this global quantum communication network, where, we have this satellite-based approach where we are connecting different ground stations. And then, this then is sending keys to, several service providers, maybe it's using fiber networks. So we want to connect fiber and satellite first within the country, and then, of course, between countries. And that is what I hope we would see in most of our lifetimes. And there are different approaches people are taking internationally towards this. Ours is called Quantum Experiments with Satellite Technology, or the QUEST project, which is a collaboration between RRI and ISRO. And as I mentioned, this started way back in 2017. And the aim is to establish information theoretically secure quantum communication over large distances and perform QKD between 2 ground stations within the country using an Indian satellite. In the process, we also have a collaboration with our Canadian colleagues, whereby we would like to explore the possibility of having a secure key between India and Canada, which would, of course, be, if successful, some sort of a distance record, which we hope we will be able to achieve. Okay, this is our portable ground stations at RRI, and this is, the Astrodome, which is where the telescope is housed and so on. So early this year, in January, February, we demonstrated free space quantum communication between 2 buildings at RRI using entanglement as a resource. And this was using an atmospheric free space channel. And that is very important because, of course, atmosphere brings in new dimensions. And so since we have been able to do this, this is the first step towards actually going towards longer distances and finally satellite. And so this again, these are our results from the in-lab demo of the entanglement based protocol. And this was the initial results for the atmospheric channel based protocol. And again, and this is something we are now optimizing. We had some lockdown and so on after that. So now we're optimizing them again. Again, this garnered a lot of appreciation from different quarters because this was again India's first demonstration of free space quantum communication using an atmospheric channel. Okay, and so we are very happy that we were able to do that in spite of the lockdown last year as well. And so these are some of the people who are involved in this experiment. And of course, this is something goes without saying, that we remain enthusiastic with or without masks. And in fact, this work, as well as the state estimation work, the quantum state interferography, were recognized by the Department of Science and Technology as one of its top major success stories in 2020. And Vigyan Prasar, has a channel called the India Science, which is our nation's science channel. So they keep track of what is happening in science. And so they also recognized our QKD work as one of the top 10 innovations for 2020, which we're very happy about. And so this is RRI, and it's the best we can show you given the circumstances. So with that, I would like to, end this talk. And so this was our last physical conference, which was in 2020 January, where we managed to take this picture. And then after that, we went into lockdown. But then we do hope that we will be going to better future offline stuff soon. So with that, I think I'm on time, Arijit, so I don't want to say any further details. So hopefully I've been able to cover a broad gamut of stuff that we are working on, taking a few examples. Yeah. So thank you very much.
Yeah, I think that was a wonderful overview of your activities at RRI. And hopefully the audience have got quite an extensive understanding of how things are propagating in the quantum communication era. So I would like to encourage the audience to put down their questions, or if they wish to ask the questions themselves, that's also fine with us. So please feel free to unmute and ask the question. Yeah, Bhargav is there. Bhargav, please.
Yeah, good evening, Professor Urbasi and Sinha. I am very happy to hear you. I'm in Bangalore only right now.
Okay.
Yeah, I wanted to visit your lab once. Yeah, I mean, maybe after some time I will intimate you anyway. Yeah, this is regarding, actually, one of the slides you said that in single shot you are able to measure the quantum state, estimating the quantum state, right? Per qubit, at least.
Yeah.
Yeah. So, okay. Usually, for any interference, when you're recording onto the CCD or any detectors, you need a certain number of measurements to estimate the phase difference between the waves, right? Yeah. How this single shot is?
No, that's a very good question. So maybe I did not clarify it at that time. So see, so that's what I said, that you do not, single shot is defined in a way that you do not need to change the settings of the experiment again and again to get different measurements. So of course, any interference experiment, you can only build statistics by taking many patterns. But then you don't change the settings in the interim. So once you have set up the experiment, in order to gain useful knowledge from an interference experiment, you will always have to measure an ensemble of patterns. But that does not mean that you have to keep changing the operator inside your setup. So that is the definition of single shot here. That once you have set it,
it's a statistical process only.
Exactly, yeah. So because otherwise, how will you generate an interference pattern with one pattern? You have to, of course, have the screen, as you perhaps know. So you have to have the screen, and the photons will go and collect at different portions, and then after some statistical number, then you will be able to make out the dark and bright and so on, right? So in order to but then you don't have to change any settings in between. That is why I said, once you set it up, you can perhaps even package it in a box, because there is no human intervention for taking different sets of measurements. That is the idea.
Oh, yeah. Okay. Because thanks actually I have, because actually I work in optical metrology. So I had that interference pattern into, I may be confusing with the any zygo interferometer is measuring the phase difference on this. Yeah,
sure. No, LIGO also that would be interesting to see if we can use QSI in LIGO. But then of course it is also a perfect interferometer to do such a. But then we don't have a quantum state as an input more so.
Another one. Are you using any spatial modes in your experiments, like phase vortices or polarization vortices, like that?
We are using spatial modes, but not orbital angular momentum.
not orbital.
No.
The special modes, in the
modes
sense
is what
the
I was
way-
talking about.
Yeah, the 3 slits kind, right?
Yeah, there need not be 3, of course, but then, to discretize the Hilbert space by using apertures, that is going to give rise to, the spatial modes of the photon, which is what we are working on right now. Yeah.
Okay. Yeah. Thank you.
Thank you.
Okay. So I think any other question anybody has?
I think Nihar Ranjan Dash has raised hand.
Yes. So Nihar, please go ahead.
Thanks a lot, ma'am, for your excellent presentation.
Thank you very much.
Ma'am, I have a simple question.
Those are the tough ones.
Ma'am, in the nonlinear optical media, that is in the optical quantum system, why the SPDC process is the efficient process for generation of entangled photon?
Are you asking why, or is it? I mean,
why it is efficient for
is
generation?
Well, so usually it will depend on the nonlinear coefficient of the material that you are choosing to do SPDC. So for instance, in SPDC, we can have very bright sources of entanglement. So actually, since you may be a student, I don't know, I hope so. So
Yes,
you can have a look at this review thing where we have actually put a table where you can see how SPDC actually gets very high brightness as well as very high fidelity of entanglement. So what happens is, so, if you now compare it with some other source, let's say a quantum dot source or something like that. So the quantum dot source, if it is electrically driven, then it can lead to brightness. But then what happens is that the single photon character is a little bit reduced. So because of this brightness, you will have more than one photon possibility coming in. So this G2 measurement, if you do, it won't have a very good dip. So you will actually not be very close to the 0. It will be a dip, but not close. So you win some, you lose some. Whereas in SPDC, what we find, that is why it is the most popular way of doing things, because you have high brightness, you have high entanglement, and also high photon purity. So, but then definitely it has an issue that it is a probabilistic source. So it is not on demand. Okay, yes, so it depends on the application, but then if you don't need on demand, then clearly SPDC is ticking many more boxes than, but then there's a lot to do in the other technologies as well. Yeah, so it is a good source of entanglement because, it is making efficient use of the nonlinearity, but then whether it is the best or not, that I wouldn't want to say. Best is anyway a debatable word.
Okay, ma'am. Yeah. Thank you.
You're welcome.
Okay. So that's the second question answered. I think any other questions from the audience?
Sharing the screen then, yeah? Should I stop sharing? No, I think...
No, it's fine. Let it be.
It's fine? Okay,
yeah. So if not, then maybe I will ask a question.
But I don't know, Arijit, has Bhargav Ram raised hand again, or is it just like it is a mistake?
I think, I don't know.
Yeah, I raised my hand. Yeah.
Oh, he did. Okay.
Okay.
Yeah.
Also Nihar, actually. Also Nihar.
Yeah.
Okay.
Bhargav, please go ahead.
Yeah. See, this SPDC process, you have the light coming out of the crystal is like a cone, right? Having a ring kind of structure.
Yeah.
And you
ring
have
is the cross section.
Yeah, cross section. Yeah. Yeah. So you have an entanglement at where the two cones are actually having, sharing the spatial position, right?
Yeah, they are intersecting.
So the intersecting points only the entangled photons.
Yeah.
The other photons are just what kind of.
So they are of course correlated photons, but then I'm actually talking about polarization entanglement here. So the particular intersection point that I defined, those are the polarization entangled photons. But the other photons are, of course, sharing some other correlations. So, by definition, because they are actually twin, photons, so they will share some correlations, but they will not be entangled in polarization. But then, you could harness some other form of entanglement from them. But then I'm concentrating on, because I'm actually talking about the type 2 SPDC process where a horizontal pump leads to a horizontal and a vertical photon. So in order to define polarization entanglement, those would be the points from which to harness the same.
Yeah. Can we increase somehow, can we increase the overlapping area? I mean,
Yes,
those two
yes.
rings can exactly overlap and you have everywhere the entangled.
No, you see, there are different, types of SPDC. So there is type 0, type 1, type 2, and so on. So the one that I showed is the type 2 one, where, this intersecting cones picture comes in. But in type 1, it is actually a different picture. And if you go for collinear SPDC, then actually you end up getting, a bit more intersection than, let's say, non-collinear. So there are different ways of doing that. But then, of course, without starting to draw on a board, it's difficult. But then you can look up this, classification. Then you will get a picture for how the entangled photons would look in these different configurations. They're not all going to look like that, of course. Yeah.
Okay. So this last time when I read that article, how that Chinese demonstrated this QKD from the satellite communication. It's a 1200 kilometers apart. They are able to detect. Is it like these two cones are two parts? I mean, 1200 kilometers apart, or how that was? I am not getting that.
Oh, no, the two cones. No. So the entangled photon source is, of course, in the satellite for them. So they are sending, they're generating the two photons, and then the photons are being sent. One is being sent to A and one is being sent to B, let's say. So, they have already taken the photons from wherever they wish, from their intersection point or whatever. I mean, we won't get into the details of what kind of source they have used, but then it is safe to assume that they have used a bright source. And so, the cone is, of course, a solution to the Selmayr equation. So if you have a look at that, then you will realize that it is basically a solution to the equation that, underlies SPDC. So the cone is a natural geometric solution to these equations. But then, of course, you just take the photons and those make their way to the ground stations.
Okay. So
cone,
cone is coming from the phase, phase relation.
The phase matching conditions. It's called the phase matching conditions. So
phase matching condition. Phase matching condition of the crystal, making in terms of cone only, right?
Yeah.
Okay. Thank you, ma'am.
You're welcome.
Okay. Any other question from any of the audience? I don't see any further questions. So maybe I can ask the question myself. So when you're talking about the satellite-based QKD, what are the challenges you anticipate in delivering secure key to one of the satellites that you have envisaged in the project? So if you can elaborate a little bit on that.
See, one of the main challenges, of course, will be, how many photons will survive, right? So we are, of course, trying to do a lot of parallel research on trying to come up with brighter and brighter sources and so on, because we do know that whatever the brightness is going to be here, it is going to be attenuated by the time it reaches. So but then, of course, one of the, the things we have to also appreciate is that QKD is not something which is going to replace normal communication. So we don't expect gigabit key rate anyway. So even if we have a smaller key rate, but then that is secure, we will use it only for such communication. As of now, that is how it is envisaged. But, there will be so many challenges in terms of, whether it is the how we are going to point it, where we are going to be, what is going to be the atmospheric condition, how will the entanglement behave? Because, while there is this demo that we have just talked about from our neighboring country, but then, a lot more work needs to be done, in theory and experiment to see what is the degradation we are expecting. And so, the challenges are not just, there are physics challenges, there are engineering challenges, and then there are also some similar, so in fact, when I start saying, I can already count in my head the number of things that one is doing in order to make this all converge. So, where we would be located is another important thing. We won't be doing it from RRI.
I see. Okay. Okay.
You know,
That's
because it is
interesting.
not the greatest place to be in terms of, you know, air pollution or whatever, right?
Okay.
So
okay.
we would, you know, so many things come in. And of course,
Right.
the main thing would be that, you know, what would be the, you know, key rate and Cuba.
Right, right.
And
right.
so very fascinating, but definitely a lot of gray hair.
So sustaining entanglement is obviously one of the very
The
big
main
challenges.
problems, yes,
Is it the biggest one? Would you say it is the biggest one, or is it? Would that be an exaggeration? Are there other challenges which are
No,
big?
I would say sustaining entanglement as well as a decent number of photons which are entangled.
Yes.
Given that we are going, you know, this very long distance.
Sure.
Right.
And in order to do that, it is not just about having a very, you know, high fidelity source or having a bright source. It's also about the, you know, coming up with the, you know, the conditions for the satellite at the ground station. And so that is over and above the, you know, the challenges which, you know, are obvious in terms of, you know, the manufacturing and the physics itself, because, and that is where, so, I mean, you know, I don't think I would like to say something is a biggest challenge. There are many challenges of equal magnitude.
I completely agree. Yeah. Okay. So there's one more question from Bhargav, I think. He's asking the experiments that you have done at RRI, you know, involving QKD, are they done at infrared wavelengths or in the visible range? So it's
in the infrared, yeah.
Infrared, right?
Yeah. Right. So it's near IR.
Near IR, right?
Yeah.
Okay. So is there any other question from the audience? Anybody wants to ask anything? Okay, I don't see any more hands or questions in the chat box. So one thing, I have been following your work quite closely, and I appreciate all the review articles that you have written, and especially the QKD SIM paper that was in Physics Applied, I think. So would you say that the QKD SIM can be implemented in an undergraduate lab to teach students? What do you feel about that?
See, the QKD SIM is, of course, a simulation toolkit, right? So then,
right.
I mean, of course, as we speak, we have currently actually just applied for a patent, so that I didn't point out. So then, so we are in the process of getting a patent for this thing. So our plan is to actually make it available on some kind of a common, platform like some GitHub or something, so
right.
that students can actually use it and learn something, and also use it for research, because QKD SIM is not just it is not an educational toolkit, although it could be. I mean, we are learning every day, but then it is actually more about being able to come up with the right conditions from all the source, transmission and receiver perspective, so that you get a desired output from your experiment. And in fact, one of the things which we are working on is actually making it broader for other quantum optics experiments as well, not just QKD.
I see.
Although it's called QKD SIM, but then it involves quantum optics elements which are beyond just QKD.
I see.
So we are working on an iteration of that as well.
Okay. Yeah. I see. Okay. So then probably maybe a couple of months later, when this patent application works out, hopefully we can expect some kind of
Yes, that is the plan, but it got somehow delayed because the patent office was also closed.
I see.
So modulo everything. So and also we have a collaborator who's in Calgary, so they had different waves and all that. So finally, we have actually converged on a certain paperwork as of last week. But then we have the patent application number and all from May.
I see.
How it is, but then it is not something I usually like. We are, academics, we like to talk about papers and all, but the patent thing is also important, of course, because then it is useful for people to just make use of. No?
Sure.
So that is the plan. Yeah.
Okay. So I think there are no further questions from the audience. Then I think on behalf of the audience, on behalf of the audience and on behalf of Camost, I would like to thank you very much for accepting our invitation and giving us this extremely informative overview on potential quantum communication technologies using photonic systems. So thank you very much once again for accepting our invitation. And hopefully you will be able to visit us soon. And we have been talking about your visit to Tirupati. So hopefully,
yes, I would like to visit you guys and other associated elements in Tirupati. I think we all need some blessing,
Right. Yes, definitely.
You just are located in the perfect spot. I think you're anyway getting blessed every day, but then,
Sure.
But then thanks a lot, Arijit and Professor Deshmukh, for this invitation as well. Of course, it was my pleasure to accept it.
We are thankful to you for accepting our invitation. What a splendid talk this has been.
Thank you very much.
Thank you very much for.
And I hope to see you all offline at some point soon.
Yes.
Definitely. We certainly look forward to your visit sometime.
Thank you. And likewise, yeah.
Right. So this colloquium series will continue even till tomorrow and day after. So tomorrow, as a general reminder, I would like to say that tomorrow we have a colloquium with Professor Dimitri Woodker, who is going to talk about quantum sensing experiments using NV centers in diamond. And then day after, we have a colloquium by Professor Peter Rudman on low temperature plasmas. So there are two upcoming excellent colloquiums, so stay tuned. And once again, I would like to thank our two directors for enabling this center and encouraging us to continue our activities, both in terms of academics and research. So thank you once again, Professor Sinha, and thanks to all the members who participated in today's discussion. So wish you all a very good and pleasant evening from Camost.
Thank you very much.
Thank you.
Thank you.
Goodbye.
Thank you. Bye.
Goodbye.
Bye. Good night.